Okay, in today's video, we're going to look at section 3.2, which is differentiability. So, question: how might the derivative of function f at a fail to exist? So, how might a derivative fail to exist? So, in the previous lesson, we saw that for a function f of x equals the square root of 3x, that f prime at 0 failed to exist. And so in this lesson, we're going to explore this concept in more detail to see if we can't predict when that might occur in future functions. So a function will not have a derivative at a point where the slopes of the secant lines fail to approach a limit. So if the limit fails to exist, so that's something to keep in mind. As x approaches a, when this happens, we say the function f of x is not differentiable at a. So if the limit fails to exist, as x approaches a, the function is not differentiable at a. So how does how do I know if the limit exists or not? Remember that the limit from the right must equal the limit from the left. And so we're going to be looking at that kind of thing. So differentiability. A function f of x is differentiable at a if the limit as x approaches a from the left equals the limit as x approaches a from the right of this difference quotient, or this form over here is the same form. Remember the two different formats? The one-sided limits must agree. If that occurs, then the function is differentiable at that point. There are four different instances where a function is not differentiable at a point, and we're going to look at those because we use those to help us see quickly, the behavior of a graph, if it's going to be differentiable or not. So the first one here, f of x equals the absolute value of x. Is f of x differentiable at 0? So let's take a look. I have that one over here. We're going to walk through this one. So remember, the absolute value of x is a V-shaped graph, something like that. Here is 0. So what is this right here? Well, this is a corner. Okay? So looking at this function right here, the absolute value, you need to keep in mind, or hopefully you remember, that the absolute value can be written as a piecewise function. And it is a negative x whenever x is less than 0. And it is equal to x whenever x is greater than or equal to 0. Okay? So that is the piecewise form of an absolute value function. So we need to find the limit as x approaches 0 from the left of f of x minus f of 0, x minus 0. Okay, so as we go through all this, from the left, what is the f of x when x is approaching 0 from the left? When I'm over here, well, I'm on the negative side, and so this is equal to a negative x. Okay, f of 0 is just 0, and this is x minus 0. And so now I have the limit as x approaches 0 from the left of a negative x over x, which is negative 1. Okay? So what is the limit as x approaches 0 from the right? Same thing. And you can see what's going to happen, I hope. From the right side, the absolute value is going to just be the x value. This will be x minus 0 over x minus 0, which is the limit as x approaches 0 from the right of x over x, which is positive 1. So because the one-sided limits are not equal, okay, the derivative does not exist at 0. So f of x is not differentiable at 0. Okay, so that's what we concluded from that. So that is a corner example. Another example would be this one right here. If you graphed this graph, x to the 2/3 power, And what does that look like? It looks like this. It'll come up like this, and it'll come up like this. Okay? And they meet right here at 0. This is called a cusp. Okay? And so, same process again. We need to check the limits from the left and the right. So this would be f of x minus f of 0 over x minus 0. This is the limit as x approaches 0 from the left, and this is going to be x to the 2/3 minus 0 over x minus 0. X approaches 0 from the left. And this is just basically going to be x to the 2/3 divided by x to the 1. So you subtract the exponents, and you literally get 1 over x to the 1/3. So as I'm getting closer and closer to 0, okay, from the left side over here, so all the x values are negative. This is a cube root. I can take the cube root of negative values. It's not a square root, it's a cube root. So what happens is this thing, these little slopes are doing what? They're getting steeper and steeper and steeper. This thing is approaching negative infinity because the x values are negative. See? Negative slope, negative slope, negative slope, negative slope, negative slope, getting closer and closer to a negative infinity. What is the limit as x approaches 0 from the right of this function? And the same process is going to occur. You'll get x to the 2/3 divided by x. And again, I get 1 over x to the 1/3. But this time, the x's are positive because we're kind of approaching from the right. So the x values are positive. All the slopes are positive here. And so this is approaching positive infinity. So from this, we can see clearly that their one-sided limits don't even exist. Okay? There is no one-sided limit here. So there's no way they can agree because they don't exist from either side. So that means f of x is not differentiable at 0. Okay? And so that's a cusp. So anytime you have something like this comes on, you know that's not differentiable at a cusp. Not differentiable at a corner, not differentiable at a cusp. Okay? So I'm going to move my notes over here so you kind of see all the little side notes that I've written. So take a moment here, pause it, write those down. Okay? And then now here's the bottom part, those two examples. So pause here and write those notes down. Okay, so let's look at another example. This is the cube root. Here the cube root was on the bottom of the fraction. Here it's on top. Okay, so what does this graph look like? We graphed the cube root before in algebra 2. It basically looks something like a big elongated S, like so, doing that. Okay, so what happens at 0? Okay, so taking our function right here, we want to look from the approach 0 from the left and from the right. So what is the limit as x approaches 0 from the left of this function? It's the limit as x approaches 0 from the left of the cube root of x minus 0, and we get the limit as x approaches 0 from this side. So this is x to the 1/3, this is x to the 1. So when I do exponent rules, I'm going to get 1 over x to the 2/3 on the bottom. Well, as this number here goes to 0, this whole thing here, and since I'm from the left, now I'm squaring it, which means it's going to turn negative values into positive values. And so this is going to go to positive infinity. As I approach it here, see these are all slightly positive little slopes here, right? So they're all positive, so therefore it's going to go to positive infinity. What's the limit as x approaches 0 from the right? x minus 0. So you can see I'm going to get basically the same thing again. Cube root 0, x minus 0. And so this is the same as that, so I'll have exactly the same thing from this direction. 1 over x to the 2/3, which again goes to infinity. And just like before, okay, even though these agree, they don't agree on a value. This is not a value, this is just a concept. So they don't even exist again. Okay. And so what we have here is we have again, f of x is not differentiable at 0. The limit has to exist, and these limits do not exist. Okay? This right here is a vertical tangent. So there is a vertical tangent right here. You can use the y-axis to represent it at 0. This is the vertical tangent line to this function at 0. Okay? And so vertical tangents have no slopes, and there you go. I have another example we're going to look at. This is a piecewise function right here. And so what does this graph look like? So at 0 right here, when the numbers are less than 0, I'm at -1. So what I have right here is I have a hole in the graph here, and then it goes off in this direction. And then I have a hole in the graph right here, and it goes off in this direction. All right, take it back. This is the equal to, so there's a dot right here. Because it's equal to 1 at 0. So this is the piecewise function that you see right here. And you can see that these are not even connected. This is called a discontinuity. Okay, remember we had that jump discontinuity? All right. And so you can see that as I go through this and show you that it's not differentiable here. I think I used the other form on this one. So you can see that being done. So we're going to do the limit as h approaches 0 from the left, and we're going to use f of 0 plus h minus f of 0 all over h. And so this is the limit from the left. This right here is going to be -1 minus 1 over h. So this is going to be the limit as h approaches 0 from the left of a -2 over h. Okay? And so use that, yeah. And so this is basically going to infinity. As this gets closer to 0, this is getting bigger and bigger and bigger. It's going to infinity. What's the limit on the other side? Of this. F of 0, h. This is going to be 1 minus 1 over h. And 1 minus 1 is 0. Okay? As I get closer and closer and closer here, there's a problem going on over here. This break in the graph is the problem. Okay, this side is approaching 0. That one's pretty obvious, but you have a hole in the graph, so you're getting closer and closer, and it's indeterminate what's going on over here. This function is not differentiable at 0. This is a break in the graph, discontinuity. Okay, this is the break. So we have the corner, we have the cut, we have the break, and we have the vertical tangent. All right, so let's take a look at this one. It's a little bit different example here. So those were the 4. So you have the corner, the cut, the vertical tangent, and you have the break. Those are the 4 major types of non-differentiabilities. Okay, so I have 2 more examples here, or it looks like I have 3 more examples to walk through here, just kind of showing you different approaches to things. So here's a function, x squared. Is f differentiable at 1? So again, let's go through this process. So the limit as x approaches 1 from the left of f of x minus f of 1, x minus 1. So x approaches 1 from the left. This is going to be x squared minus 1. And then we can use our limit technique of factoring. This is x plus 1, x minus 1, x minus 1. These will reduce out, and I have the limit of x plus 1. Now I can do direct substitution approach. It gets the number 2. What's the limit as x approaches 1 from the plus side? And you will see that you're going to get basically the same thing. So this is going to become, as I factor and reduce out, I get exactly the same thing as I had on the other one. And direct substitution gives me a 2. And so because these are exactly the same value, okay, remember, this is the derivative at a point from the left, from the right. They agree, so the limit does exist. I can say, excuse me, wrong function name, f prime at 1 equals 2. Okay? Is this differentiable at 0? Okay? And so what is the square root of x? Right there, it looks like that. So let's take the limit as x approaches 0 from the right. I go through all this. It approaches 0 from the right. I'm going to get the square root of x minus 0, x minus 0. I'm pretty sure hopefully you saw something that was kind of obvious, but we'll talk about it here in just a moment as I go through this. And then again, if you use exponent rules and stuff like that, you're going to get 1 over the square root of x, which is approaching infinity. So the little slopes here are all positive, and as they get closer, okay, it's going to turn into a vertical tangent. We kind of talked about this one before, but let's look at it this way. In the differentiable aspect of things, I have to show that the limit exists. Well, the limit will exist here if the limit from the right and the limit from the left agree. What's the limit from the left? There is no limit from the left. There's nothing over there. So I can't compare the two because they don't exist. Okay, so that's one of the things you can kind of look at on this one. Another approach to this thing here. Let me go ahead and show you my full notes here, and you can pause and take and get all the little side pieces down. This way. So you can pause there, copy that. And you can pause here to copy that. Okay? So again, right here at the end, you can't take this limit because the function does not exist there. So h of x is not differentiable at 0. There's a vertical tangent there. So we've talked about this vertical tangent here. This is 1/2 of the cusp also. Okay? I'm going to take a look at some other stuff over here. All right, so let me put it right here. So some things to keep in mind when determining if a function is differentiable at a point. If a point is not in the domain of the function, then it is not in the domain of the derivative function. If f of x equals this, its domain is all the real numbers, x cannot equal 0. Here's another one for natural logs. Okay, all the real numbers, x has to be greater than -1. What makes that 0 is -1. And then the piecewise function right here. Okay, the domain is all the real numbers, x is greater than or equal to 0. 0 is the smallest value in this function. There is nothing smaller than that. So all of these functions have values excluded from their domains. So f prime at 0, g prime at -1, h prime at -7 do not make sense. Okay, so pay attention to the domain of your function so that you don't fall into the trap of trying to find these things when they don't exist. Okay, here's another example. Is this differentiable at 1? This is the last example that I have down here. So just like before, we go through the process here. If it is differentiable, then we're going to look at the limit from the left and the right and see what happens. Okay, so look closely at it. Okay, here we go. So the limit as x approaches 1 from the left of g of x minus g of 1 over x minus 1. This is the limit as x approaches 1 from this side to here. So I'm approaching 1 from the left side, so that would make this a 2x. G at 1, okay, 2 x minus 1. I can do a factoring technique. And I get 2 times x minus 1 over x minus 1. And I get the number 2. Take the limit as x approaches 1 from the positive side. Okay, and you go through this again. X approaches 1 from the plus. Now I have x squared plus 1 minus 2 over x minus 1. And x approaches 1 from the plus side. And you clean all this up. This is going to be x squared minus 1. So that factors and reduces and gives me x plus 1. And so direct substitution gives me a 2 again. So if you look at this, you'll see that I have a 2 here. Okay? But this function is not differentiable at 1. Why? Okay? Why is that true? Well, kind of tricked you just a bit. If you look at it, there is no value at 1. I kind of tricked you because I said, well, what's g of 1? And I put a 2 in here. Kind of tricked you a little bit. Because if I plug 1 in here, I'm going to get 2. If I plug 1 in here, I'm going to get 2. So that's why I kind of did that to you. But if you look at this part right here, there is no or equal to here. X cannot equal 1. It's not in the domain of this function. So there cannot be differentiable there because there is no value there. Okay? So be careful of that. See, I went through this whole process. It looks like it's going to be differentiable at 1, but when actually the function itself did not exist there. So something to be careful of. It happens quite often, tricking people out. So here's this page right here. If you want to pause and copy that down. Okay. And then here's the last part down here. Very, very important. When determining the differentiability of a function at A, consider the following. Make sure the function is defined at the point before you go to the limits. That was the last example. Make sure it's actually defined there. Make sure that there are no discontinuities at the point. Look at the graph if you can. Consider the 4 types of non-differentiabilities: corners, cuts, vertical tangents, and discontinuities. See, for a vertical tangent, it could exist there. Everything could be fine, okay? But if you can see that it's going to be a vertical tangent, you can save yourself a lot of time. And then this is probably one of the most important things right here that's in the box. Very, very important. Always remember this. Differentiability implies continuity. This is a connection between differentiability and continuity. We talked about continuity last time in the previous lessons. Okay? Just because it's continuous does not mean it's differentiable. This is continuous. It's not differentiable at the corner. This is continuous. It's not differentiable at the corner. This is continuous. It's not differentiable because of the vertical tangent. But if a function is differentiable, then it means it will be continuous. Okay, so this way is very important. It's false the other way, but it's true this way. Differentiability implies continuity. They question you this all the time on the AP exam to make sure you know that. If a function is differentiable at a point, then a function is also continuous at the point. The converse is not true because of the corners, cusp, and vertical tangents that I just showed you. Very, very important. Make sure we know this. And so that concludes this video.